Hello, everyone. In this video, we are going to cover the notes and examples from section 3.1 on the definite integral. As you saw in some of our previous video assignments, the integral of a function tells us about the accumulated change of a function. We can also interpret integral as the area under the curve of a function. So if we have a function, just draw here a rough sketch. So if we have our function that we'll call f of x, and let's look at f of x on the interval from a to b. Then if we compute the integral from a to b over f of x dx, this value is equal to the area under the curve between a and b. So in this section, 3.1, we're going to look at some strategies and techniques for computing that area. So let's get started. So we are told here that for each problem, approximate the area under the curve over the given interval using 4 left endpoint rectangles. You may use the provided graph to sketch the curve and rectangles. So let's look at this example together. So to get a sense of what's going on, first let's graph our function. So here we see that our function is a line, a linear equation. We could rewrite our function y equals -1/2 times x plus 5. And now we might recognize it more in that slope intercept form. So what would the graph like? Well, when x, the input, is 0, the output would just be 5. And we see that's the vertical or y-intercept is at 5. So we see that slope is -1/2. So to draw the rest of our line, 1 is our rise, and we can rise in the negative direction. So if we go down 1/2, down 1/2. And similarly in the reverse direction. So we can rise 1 and go to the left 2. All right, so we can fill in our line here. Or sketch in this curve. Okay. So for this problem in particular, we care about the area under our curve between the points -5 to -1. So let's draw that in as well. So we're looking at -5 to -1. All right. So the idea here is that we want to estimate this area under the curve. And now we see this shape that's formed is just a trapezoid. So we could compute the area explicitly, but in this problem, we want to get some experience approximating areas under curves using rectangles, because it might be that our curve isn't so pretty. All right. So let's get started by first separating our interval, -5 to -1, into 4 rectangles. In order to do that, we need to determine the width of our rectangles. And let's get it off shape here. So width. So notation, we often refer to the width as change of x, or delta x here. And that width is going to be equal to, well, the total distance or length of our interval. So that would be b minus a if our interval was a to b, divided by n, where n is equal to the total number of rectangles that we are using. So for us, that looks like our change of x is equal to -1 minus -5 all over 4. So being mindful of our parentheses here, subtracting a negative would make that a positive. So we get -1 plus 5 in the numerator over 4. which becomes 5 over, oops, not 5, rather 4 over 4, which is 1. So the width of our rectangles are just going to be 1. So if we were to draw in just the widths of these rectangles here, we'd see that they fall pretty nicely in with these grid lines. So we'd have width here, 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 and here. And we see that if we count them, we have 1, 2, 3, 4 rectangles, or 4 widths that will fill in for our rectangles. So in these problems, we're asked to estimate the area using a left endpoint rectangle. So that means when we want to draw in our rectangles, how high, or rather when we're asking the question, how high do we draw in our rectangles? We're going to draw them in so that the left side of the rectangle hits our function. So I'm going to make that point big. And so my first rectangle here will be the height that happens or that appears at that left endpoint of my rectangle. So that's the function value on the left end of the rectangle. So I'd have one here too. And another one here. And our final one here. Okay. So now what we want to do is compute the area of all of these rectangles. So if we look at one rectangle in particular, and I'm not looking at a particular one, but just in general, the area of a rectangle is going to be how tall the rectangle is multiplied by the width. Recall area is length or height, we'll call it, by width. So for us, what are these heights and widths? Well, we can determine the width. We've already done that. That's going to be the change of x. And the height, well, the height is going to be the function value on the left endpoint. So let's call it f of x, where this input here is a little x. So we need to do this across all of those 4 rectangles that we just found, or that we just drew. So let's do that together. And let's first find the area of each rectangle. So to do that, let's make a table where what we're going to input is the x value that we're using to determine that height. And then on the other side, let's find our area. So that would be our change of x times f of x. I'll call it x twiddle because that x is going to change depending on what interval we are over. So first, let's write out what are those 4 endpoints we are going to use. So if we look at our graph, well, we're going to use 5 as an endpoint. We're going to use negative 5 rather, negative 1/4, negative 3, and negative 2. So I'm going to write that in. Negative 5 will be an endpoint, negative 4, negative 3, and negative 2. So now for each of these areas, the width is going to be the same, and that is 1. We already computed that. So I can just fill in the width for all of these areas. And so now I need to compute the function output value at each of those endpoints. So we have the rule for our function up here given. So to find that height of the first rectangle, well, I need to plug in negative 5 into x. So that would look like minus negative 5 over 2 plus 5. And then we can do this with, we'd continue rather with each of the remaining left endpoints. So we'd have negative 4 over 2 plus 5, negative 3 over 2 plus 5, and negative 2 over 2 plus 5. So let's compute each of these. So each of these products has a 1 as a term. So if we multiply anything by 1, it just It goes away, so we can just ignore that. And then write this as negative 5 over 2. So negatives cancel out, and we just get 5 over 2 plus 5. And we get 4 over 2 plus 5. And we get 3 over 2 plus 5. And finally, 2 over 2 plus 5. So we can simplify here. 5 over 2 is just 2.5 plus 5. 4 over 2 is just 2. So we get 2 plus 5. 3 over 2 is 1.5 plus 5. 2 over 2 is just 1. So we get 1 plus 5. And then combining these final sums, first rectangle then will have an area of 5 plus 2, which is 7.5. 5 plus just 2 is 7. 5 plus 1 plus a half is 6.5. And then 5 plus 1 is 6. So now what we're going to do is add up, after finding the area of each rectangle, we're going to add all areas. So for that, we're going to get the sum of the areas here. So we could do that in our calculator or look strategically. So we see that we have 1/2 plus 1/2 gives us 1. So this really is 6 plus 6 plus 7 plus 7 plus 1. So we have 6 plus 6 plus 7 plus 7 plus 1. 6 plus 6 is just 12. 7 plus 7 is 14 plus 1. So now we can add 12 plus 14. It's going to be 26 plus 1 is going to be 27. So then we can estimate the total area under the curve from these rectangles. And we can say that the area of the left endpoint rectangles is 27. And we're not given a unit measurement here, so we could just say 27 units squared.